So today we're going to be talking about percent composition. Now specifically we're going to be talking about it for chemistry-wise, but don't forget percent composition can be applied to many different levels of activities across all kinds of disciplines. You could say that what is the percent composition of a pizza, right? And you could say what 50% of the pizza is cheese, 20% of the pizza is sauce, 30 and then 30% of the other part of the pizza is dough. Now if I add pepperoni, then you're adding another component, and that's going to change the ratios of the other three components. So you have to be specific on, how are we going to measure this? And the easiest way, or one of the easier ways, is to do it by parts per hundred, or percentage-wise. And the other easy way that we can do it for chemistry, especially for compounds, is to use the mass. Since we know how to calculate the molar mass of elements, and we know how to calculate the molar mass of compounds and formula units, we should be able to find out what percentage of each element makes up the total compound molar mass. And the reason why we do this, because this is going to help scientists understand what compounds they're using. Don't forget, there are several different versions of iron oxide. There's iron 2 oxide and iron 3 oxide. Both will have different percent compositions of each element. So by understanding what the percent composition is for each element in a particular compound, you will be able to determine what that compound is. And there's some examples down here. So the goal of today is to kind of teach you how this works. And I've given you the formula here. Percent composition by mass is the mass of the component, what you're trying to find, or the part, divided by the mass of the compound, or the whole, times 100%. So let's think back to what we did today in class with the Oreo cookies. Now remember, the Oreo cookies, our goal was to determine what the composition of each cookie was, and then use that information to determine whether or not the double stuffed version of the Oreo cookie indeed had double the stuff, right? So the cookie was made up of two components, as you recall, the cookie itself, the hard crunchy cookie, and the cream filling, right? And in the double stuff, you can see here that the cream component looks like there's a lot more cream in the double stuff than the original cookie. So you would expect that the mass of the cream part of the double stuff to be different than the mass of the original cookie, and therefore the percentage that mass of cream brings into the total compound of the cookie, or the total cookie weight or mass, to be different than the original. And by understanding the percent composition of each one of the cookies, you could better describe the cookie to a person without having ever seen the thing. So you could say, well, this particular cookie is 25 mass percent cookie and 75 mass percent cream, and this cookie here is 45% by mass cookie and 55% by mass cream, right? Those are totally different cookies, because now you know that one has more cream than the other. And by doing the percent composition on the cookies, you can determine which one would have a higher percentage of cream, a higher percentage of cookie, whatever. But without that understanding, you really can't make that decision or that claim. So how does the cookie activity help us understand percent composition for chemical compounds? Well, let's look at two chemical compounds that can be represented by our two cookies. Our first chemical compound is water, H2O, right? And I'm going to say, in this case, that we have two hydrogen atoms, which we do, and one oxygen atom. And we're going to represent those atoms individually by the parts of the cookie. So my first part is one hydrogen atom is going to represent one cookie shell, and the other one is the other cookie shell. And my oxygen is going to be represented by the cream. And in my second case, H2O2, the only difference in composition is that I have an extra oxygen atom in the backbone for water, right? So H2O, H2O2, so I have 2 oxygen atoms, right? So I'm going to do the same thing. Everything's represented by the same. My 2 cookie shells are the hydrogens, but now I need to represent the double layer of oxygens, or the 2 oxygens, by this thicker layer of cream. So far, so good. Now, how would I understand to get the percent composition of the cookies by mass, right? I would weigh the total mass of the cookie and then weigh each component of the cookie, in this case the cream and the 2 cookie shells. And by doing the percent composition formula, which is percent composition equals the mass of the part divided by the mass of the total times 100%. So I would get the mass of the total cookie divided by, in this case for the cream, we would measure the mass of the cream. So the cream mass divided by the total cookie mass times 100% would give me the percentage of the mass that's by the cream, right? And you could do that over here too. Well, the same basic principle applies to a compound, except instead of measuring the mass, we're going to use the molar masses of the individual elements to determine our molar mass of our compound. And that same molar mass of each individual element times the frequency of that element in the compound to represent our contribution by mass of the compound. So in the case of H2O2, I would find the molar mass of this whole system, and then that would be my total. And then if I wanted to find the percent composition of the oxygen part, I would get the mass of each individual oxygen atom by molar mass of that. So that would be 16. There's 2 of them, so that's 32. 32 grams divided by the total molar mass of that, which is 34 grams. I've already done the math. So it would be 32 divided by 34 times 100%. And in this case, it would be 18 grams per mole is my total mass of my water molecule per mole, but 16 grams of it is the mass of the oxygen content of that. So it would be 16 grams per mole for the oxygen part, divided by the total, which is 18 grams per mole, times 100%. And if you did that math, you could see whether or not there's twice as much percentage-wise of oxygen in this compound than there is in this compound. Same is true with any compound. Okay, so let's quickly look at a couple examples here. I spent a little bit more time on that last slide than I should have, but hopefully this will make you run through this real quick. What is the percent composition of potassium chloride for each element? Again, there's 3 steps we need to do. Determine the mass of each element in the compound using the element's molar mass. We use our periodic table to look those up, and I've looked them up already, and I said that potassium is 39 grams per mole, and my chlorine is 35.5 grams per mole. Again, we're going to have to make the molar mass of the total compound. So that's just the number of elements of that particular species times its molar mass, and then you add them together. So there's only 1 potassium, so there's that. 1 chlorine, there's that. When we add them together, we get 74.5 grams. Now, the last step is that we haven't done yet, or haven't had a lot of practice on, is to divide each component's mass portion by the total molar mass of the compound, and then multiply the decimal fraction by 100% to get the total percent composition. So we have 39 grams of the per mole is potassium. My total molar mass of potassium chloride is 74.5. So 39 divided by 7.5 equals 100%. We get 52. And for the chlorine one, it's the same basic principle, except now we have to substitute the chlorine molar mass, because that's what we're looking for, divided by the total. Again, we get 47.7, right? And so it's this basically, that's the approach you take, right? This is the part, this is the whole, times 100%. in our example 2, this is a little more complicated, but it's the same basic principle. In this particular compound or formula unit, we have 3 different elements, and some of those elements appear more than once in the formula, right? So if you look at the formula closely, we have magnesium, oxygen, and hydrogen are our elements, but the oxygen and hydrogen appear twice in the compound or contribute twice to it. There's 2 atoms of oxygen and 2 atoms of hydrogen for every 1 atom of magnesium. So again, it's the same basic principle. Step 1 is to determine the total molar mass of each element using the molar element's molar mass. And so I've done that here, right? And if you don't know how to do that yet, you should go back and practice how to calculate molar mass. I'm going to sum them up to get the total molar mass of the total compound. That's here. I'm going to divide each component's mass portion by the total molar mass of the compound, then multiply it by 100% to get the percent contribution. So in this case, right, even though that magnesium is the heaviest or the more massive or has the highest mass of all the other two elements, right, since it's not it only has 1 atom per molecule and oxygen has 2, oxygen is actually bringing in more mass component to the compound than the magnesium. Even though magnesium has a higher molar mass, because there are 2 oxygen atoms, I'm bringing in more mass due to the oxygen than I am doing the magnesium, and that's why you see a higher number here than here. Again, even though that the molar mass of magnesium is higher than the molar mass of oxygen. Right? So it's not just the molar mass that you have to be concerned with, it's the molar mass and the frequency of that particular atom in your compound that determines the percent composition or percent weight of that element in that compound. So if you've paid attention to any other of my videos, we always have a you try it thing at the end to see if you've mastered the quick concept here. So what you're going to do is kind of stop the video again, write down the little tables here, calculate the percent composition that each element here brings into the compound. So sodium, oxygen, hydrogen, I listed them here. And in this case, we have 4 elements, nitrogen, hydrogen, sulfur, and oxygen. I listed them here. Calculate the composition, percent composition. Remember, you're going to have to look up the mole or determine the molar mass of each one of these, and then determine the molar mass of each one of these, and then do your calculation. So when you're ready, stop the video, copy the information down on the slide, work through the problems, and then be ready to answer your video. Be ready for the answers and start the video again. So stop the video now. So here are the answers, and there are 2 common pitfalls if you didn't get these answers. If you did get these answers, you're good to go and you can stop the video and move on. But the other areas that you have to be cognizant of if you didn't is that make sure you calculated your molar masses of your 2 compounds correctly. So I give you the 2 here for this and this. And the second thing is that you need to understand that it's not just an atom's molar mass that contributes to the overall molar percent composition value. It's molar mass times the frequency of that element in the compound. So for example, in this compound, we only have 4 elements, right? And if you looked up the molar masses of all the elements, sulfur is the highest molar mass. Nitrogen is 14, hydrogen is 1, sulfur is 32, and oxygen is 16. But in the compound, because there's only 1 sulfur atom and there are 4 oxygen atoms and 8 hydrogen atoms and 2 nitrogen atoms, it's a weighted average. In other words, you've got to account for the frequency of that atom times its molar mass to get the mass contribution of that atom in the compound, right? So in this case, we know that sulfur is 32 grams per mole, right? And oxygen is 16 grams per mole. So by molar mass weight, you would think that the sulfur content or the sulfur percent composition is higher than oxygen, but we are bringing in 4 oxygen to every 1 sulfur. So we then need to make sure that we multiply the molar mass of oxygen by 4, and when we do that, we can see that the molar mass component of the oxygen contribution is much higher than the sulfur one, and it's reflected down here. So that's it. If you got these and you're good to go, you can move on. If you still struggle, find me and I can help you out.